Hello, everyone. I just want to come back to the idea of the existence of limits. So last time we talked about different limit laws, and you can calculate the limit of a function using limit laws. In addition to that, we can calculate the limit or find the limit of the functions using the idea of the existence of limits. So again, the existence of limit is that a two-sided limit exists if and only if both one-sided limits exist and are equal. So that is the limit of the functions as x approaches a equal to L exist if and only if the left-hand limit equal to the right-hand limit and they are equal to the same value L. We're going to take this concept and work on some example. I have shown this example before, but let's go back and take a look at this particular example. So the example is that show that the limit of the absolute value of x as x approaches 0 is equal to 0. Absolute value of x is the piecewise defined functions. That is, absolute value of x is equal to positive x if x is greater than or equal to 0, and is equal to negative x if x is less than 0. So now when you find the limit of the function at x approaches 0, you need to consider the left-hand limit and the right-hand limit because the function has two different parts to it. So that means when you consider the limit of the absolute value of x as x approaches 0 from the left is actually equal to the limit of negative x as x approaches 0 from the left, because we just want to consider the value of x on the left-hand side of 0 or x is less than 0. If you use direct substitutions property, this gives you 0. On the other hand, when you find the limit of the absolute value functions as x approaches 0 from the right, so you, in this case, you can see the value of x that is on the right of 0. So this equal to limit of positive x as x approaches 0 from the right. And again, if you apply direct substitutions, you get this is equal to 0 as well. So from these calculations, it showed that the left-hand limit equal to the right-hand limit and equal to the same value. And therefore, you can conclude that the limit of the absolute value functions as x approaches 0 is equal to 0. Now, moving on to the next example, we're going to apply similar idea that the limit of the function exists if and only if the left-hand limit equal to the right-hand limit and equal to the same value. So for this function, you have absolute value of x over x. You remember from the previous example, absolute value of x is the piecewise divided function. So it breaks down into two different parts. So that is absolute value of x over x is equal to positive x over x if x is greater than or equal to 0, and is equal to negative x over x if x is less than 0. At this point, you can simplify the functions. So x over x is equal to 1 and negative x over x is equal to negative 1. So this piecewise defined functions becomes positive 1 if x is greater than or equal to 0 and is equal to negative 1 if x is less than 0. Now, when you consider the limit of these functions, again, you need to consider the limits, the left-hand limit and the right-hand limit. So the left-hand limits, so limit as x approaches 0 from the left of absolute value of x over x. So this is the limit as x approaches 0 from the left of negative 1. Again, x approaches 0 from the left means that you consider x values on the left of 0. Right. So this gives me negative 1 because the limit of the constant is the constant itself. Next, we consider the limit of the absolute value of x over x as x approaches 0 from the right. That means this is limit as x approaches 0 from the right of +1. So this is equal to +1. All right, from these calculations, it shows that the left-hand limit does not equal to the right-hand limit. And therefore, you draw a conclusion that the limit does not exist. So since the left-hand limit does not equal to the right-hand limit, then limit of absolute value of x over x as x approaches 0 does not exist. So I hope these two examples help you understand the concept of the existence of limit. Again, the limit exists when the left-hand limit equal to the right-hand limit and equal to the same value. So in addition to the basic limit laws that we learn in this existence of limits, there's another theorem that we want to look at. It's a very common approach in finding the limit of certain functions. It's called the squeeze theorem. So for squeeze theorem, it say that if you have three different functions, f of x, g of x, and h of x, and these functions are set up in a way that g of x is bounded below by f of x and bounded above by h of x. Then if you want to find the limit of g of x as x approaches a, you need to show that the limit of f of x equal to the limit of h of x equal to the same value. Then and only then you can calculate the limit of g of x as x approaches a. So we have the theorem. If g of x is bounded below by f of x and bounded above by h of x, when x is near a, and that limit of f of x as x approaches a equal to the limit of h of x as x approaches a equal to the same value L, then limit of g of x as x approaches a is also equal to L. So this theorem, the squeeze theorem, is particularly useful for certain type of functions that contain sine and cosine in the formula. For example, we want to show that the limit of x squared times sine of 1 over x is equal to 0. So if you use direct substitution for this limit, you will get some indeterminate form. Right. And again, when you have indeterminate form, it doesn't mean the limit does not exist. It just means that you need to do some manipulations in order to obtain the limit. Okay. So in pre-calculus, we learned that sine function and cosine function is bounded between -1 and 1. So that is, we know that sine of 1 over x is bounded between -1 and 1, right? So this creates the three functions, f of x, g of x, and h of x, right? And to get the function x squared times sine of 1 over x, I'm going to multiply every term in this inequality by x squared. So that means I get, this is -x squared less than or equal x squared times sine of 1 over x less than or equal to x squared. Now, in order to find the limit of g of x, I'm going to apply limit as x approaches 0 for every term in this inequality. That is, I have limits of -x squared as x approaches 0 less than or equal to the limit of x squared times sine of 1 over x as x approaches 0 less than or equal to the limit of x squared as x approaches 0. Okay. Now you have this is the limit of the function f of x. This is the limit of the functions h of x. And you can use direct substitutions for those. For this particular limit, by direct substitutions, you get the limit to be equal to 0, less than or equal to limit as x approaches 0 of x squared times psi of 1 over x, less than or equal to the limit of x squared as x approaches 0. Again, if you use direct substitutions for this limit, you obtain 0. By the squeeze theorem, we get that the limits in the middle, limit of x squared times psi of 1 over x as x approaches 0 is also equal to 0. Right. Similarly, in the next example, we want to find the limit of the function x times cosine of 1 over x, and we want to show that this limit is equal to 0. Right. So this function x times cosine of 1 over x, if you use direct substitution right away, you will have indeterminate form. In the case that you need to further analyze the limits, that means you need to do some manipulations to find the limit. So again, we know that cosine function is also bounded between -1 and 1. That is, so we know that cosine of 1 over x is bounded between -1 and 1. And to obtain the functions x times cosine of 1 over x in the middle of this inequality, I'm going to multiply x for every term in the inequality. I obtain -x less than or equal to x times cosine of 1 over x less than or equal to x. Now, to find the limit, you take the limit as x approaches 0 for every term in the inequality. This will give me a limit of -x as x approaches 0 less than or equal to the limit as x approaches 0 of x times cosine of 1 over x less than or equal to the limit as x approaches 0 of x. For these two limits, limit of -x as x approaches 0 and limit of x as x approaches 0, you can use direct substitutions, which give you 0 less than or equal to the limit as x approaches 0 of x times cosine of 1 over x less than or equal to 0. Then by the squeeze theorem, we have that limit of x times cosine of 1 over x as x approaches 0 is also equal to 0. I hope this helped, right? So for this particular video, we look into some example related to showing the existence of limits and to find the limit of functions using squeeze theorem. Please let me know if you have any questions.